So let's talk about the last carry propagate adder that we're going to discuss in this chapter. So this is called the prefix adder. Now, a prefix adder has generally the same goal as a carry look-ahead adder, in that it's trying to calculate the carries as fast as possible. But different from the carry look-ahead adder, it's trying to calculate these carries for each of the columns as fast as possible. So the carry in C sub I minus 1 for each column I is, we're trying to compute that as fast as possible with a prefix adder. And then we're going to use those carries that we've produced, again for each column, to use the to do the usual sum calculation, sum equals AX or BX or CN that we've done before. So the prefix adder computes all these carries, C sub I minus 1, by, well, first computing generates and propagates for 1-bit blocks. So these are just our column propagates and generates. And then we're going to kind of divide and conquer and group them into groups of 2, and then 4, and then 8-bit blocks until all of the carry ins are known. And G sub I, this generate for column I, is the carry, the carry for that column. So G sub I is going to be the carry out, or C sub I, of that column. This calculation takes log base 2 of n stages, so it is going to be faster. So a carry out can be generated by either generating the carry in a given column, or that column propagating a carry from a previous column. And I like to think of this in terms of left groups and right groups. So here's a left group of bits and a right group of bits. How can we generate a carry coming out of this now combined group left and right? Well, we could either generate it in this left group or generate it in the right group and propagate it through the left. And it gets propagated through the left. And so we can write this as, well, generate for this entire group left to right is going to be, well, either generated in the left group or generated in the right group and propagated through the left group. And so one important thing to note about prefix adders is that column -1 holds the carry in. So generate of -1, whether there's a carry generated in that column, well, it's equal to carry in. So if carry in is 1, that column, right, the -1 column generates that. So G sub -1 is equal to the carry in of the entire adder. But as you'll notice, that there's nothing to the right of that column, and so it doesn't really matter about propagate. If we look back at our left and right kind of analogy, this left one either generates or the right generates and propagates through the left. So we actually don't care about the propagate signal for that right group when we're calculating whether that group combined generates. And so P sub -1, we don't use it. It's a don't care because we don't use it. Okay, so a carry into column I is equal to a carry out of column I -1. So this carry out sub I -1 is equal to generate sub I -1 all the way down to that -1 column, or that carry in column. So does anything generate a carry from that entire span from I -1 to -1? And then we can use these. These are called the prefixes. G sub I -1 to -1. Again, that's a 1-bit signal. We can use them then to calculate our sum bits S sub I, because remember this is C sub I -1, the carry out of column I -1, and the carry into column I. So our goal is to quickly compute these prefixes, G sub 0 to -1, G sub 1 to -1, G sub 2 to -1, and so forth, all the way down to -1, So if we can get our carry out, remember C sub 0 is G0 to minus 1, C sub 1, C sub 2, and so forth. A prefix adder will generate a carry within its own block if it generates a carry in the left block or upper block, G sub L, or generates it in the right block, G sub K minus 1 to J, and propagates it through that left block. So this block I through J will generate a carry in and of itself if it generates it in the left block or generates it in the right and propagates it through the left. Likewise, this group of columns I through J will propagate a carry. If it propagates it through the right, we don't know if there's a carry in, but if there's a carry in, it will propagate that carry all the way to the output if it propagates through the right group and propagates it through this left group, I to K. And so we can state it again. A carry will be generated within a block I through J if the upper part, which I call the left part, generates the carry, or the upper part propagates a carry that was generated in the lower part or in the right part. And a signal will be propagated through this entire span I through J if it gets propagated in the upper part and propagated in the lower part. Upper part and lower part. So let's do a brief example of the prefix adder. We'll start with our columns. So let's say we have some number that we're adding together. Here's our A value, and here's our B value. Oh, let's make that a 0. And then we'll make our column 0. So here are our column numbers. Column 0, column 1, column 2, column 3, and then we have our column sub minus 1. Let's write our G sub i's and P sub i's. So generate for this G sub I minus 1 is going to be the carry in value. We can choose what that's going to be. Let's make it a 1 for kicks here. So carry into the entire circuit, so that would be our 1 that's coming up here to be carried in. And then we're going to say, okay, let's calculate G's and P's for each of the columns. Generate for the column 0 is 0, 1, 0, 0. P sub I is going to be 1, 1, 1, 1. And then this is a don't care for column 0 or column minus 1. Okay, so now we've calculated our single column or 1-bit propagate and generates for our columns. They're all 1-bit. Propagate and generates are always 1-bit, but we've calculated our G's and P's for the columns. And now we want to take, so we have a group of 1 bit wide, and now we want to say, well, now let's group these together and say, well, I want to calculate for 2-bit groups, 2-bit wide groups. So we want to calculate for column 0 and column minus 1, column 1 and 2, column 3, and we don't have a 4, but okay, so now we'll say, okay, now we're going to say G, so 0 to minus 1. We want to see if this entire span in and of itself would generate a carry. And so that's going to be, well, this left group is G sub 0, this is GL, and the right group is G sub minus 1. And so that's going to be, well, the left group, G sub L, or G sub R and P sub L. So G sub L is G sub 0. Well, we know that's a 0. But G sub 0, or P sub L, which is P sub 0, and G sub R, which is G sub minus 1. Right, so it's going to generate a carry out of this entire 2-bit span if it generates it in column 0 or generates in column -1 and propagates it through column 0. And so we can see in this case we have, well, let's see, we have G sub 0. Well, yeah, it definitely doesn't generate anything in that column. So we put a 0 for that. We already calculated it though. G sub 0 down here is 0. And so we put 0 in for that. Didn't generate it in that left column. Or, well, it could have generated it in that right column, which is in this case is G sub minus 1, which happens to be the carry in, which is 1, and propagated it through the left. Well, what's that? Propagated through G sub 0, yep. Through column 0. So that's 1. And so this group, in fact, in and of itself, generates a carry. Well, it's a little bit, right? We actually are including the carry in. We go all the way down to the carry in column. Okay, so we get equals 0 or 1 and 1, which is 1. And in fact, we get a 1 because we had that carry in. And we know that that group from -1 to 0, in fact, so we have this is equal to, remember, C sub 0. In fact, it does, column 0 does generate a carry out. Okay, so we can do this for the other blocks as well. Try to get rid of some of the clutter here. And so let's see what we do. So we had GL, the left and the right. We're going to do the same thing for the other blocks. We'll just do it for this next block. Here we have our left, and here we have our right group. We calculate it for the one column, right? We calculated the P's and G's for each of those columns, and now we're going to calculate the block from column, in this case, right? We have column 0, we have column 0, 1, 2, and 3. Now we're going to calculate it for column 2 to 1. So G 2 to 1. We want to know if that group generates a carry or not. So G2 to 1, in and of itself, does it generate a carry? So let's see. Well, this would be G sub L. All right, G sub L in this case is G sub 2, or G sub R generates in the right column, G sub R, and propagates through the left. Okay, so let's put those numbers in. Equals G sub 2 or G sub 1 and propagates through column 2. Well, so we've calculated those column propagates and generates, and so we're going to get equals G sub 2. Well, G sub 2, yeah, it definitely doesn't generate anything in that column. So equals 0 or G sub 1. Yep, that column does generate carry. And P sub 2. Yep. So this one also generates it in column 1 and propagates it through column 2. And so we get 0 or 1 gives us a 1. And we can also calculate our propagate signal for column 2 to 1. P2 to 1 is equal to, well, propagate to the left, which is 2, right? P sub L and P sub R, which is P sub 2 and P sub 1. We get, well, yep, both those propagate and propagate. So 1 and 1. So if a carry came into this group of columns 2 to 1, then yep, this is I to J, right? If a carry came into that group, it would get propagated to the output. And in fact, that group in and of itself is going to generate a carry. So we already know that that group will generate a carry in and of itself. Okay, so now let's look at our, we have our G0 to -1 was 1. I'm going to erase some of this detail that we derived it with. And we also know that G2 to 1 and P2 to 1 are both 1. Okay, so let's write those kind of summary values down. So we know that columns 0 to 1, 0 to -1 generate a carry. And that we already have one of the prefixes, right? This is C sub 0. We already got all the way down to -1. This one didn't get all the way down to -1 yet, so we don't have that prefix yet, but it'll help us in a moment to calculate the prefix. Okay, so we know that this is 1, and we know that the G sub 2 from column 2 to 1 is a 1, and P 2 to 1 is also a 1. Okay, so now we can use these two groups to calculate groups of 4. Now we have groups of 2, 2 to 1, and 0 to -1. And now we're going to use that to calculate the propagate and generate signals for that group of 4. Okay, so we're going to say, well, P2 to -1, and we have a group of 4, column 2, column 1, column 0 to column -1. We're going to use that to figure out the propagate and generate signals for that entire group. Well, propagate signal doesn't really make sense because it's the rightmost group, so we're just going to calculate the generate signal. That's a subtlety that we'll come back to in a bit. But G 2 to -1 is equal to, well, that same general equation. The left group either generates it, so this group 2 to 1 generates it, or the right group generates it, and the left group propagates it. Okay, let's put our numbers in here. So this left group is G2 to 1. And so we have the P of that 2 to 1, that left group, and generated the right group. Our right group is G0 to -1. Okay, so we want to know if this entire span now from 2 to -1 will generate a carry. Okay, well, let's see, G2 to -1 is 1, so we get equals 1, or G0 to -1, which is 1, and P2 to 1. Well, P2 to 1 is also 1. So either way, right, either by getting this carry that was generated in the right half and propagated up through the left half, or our left half generated a carry in and of itself. And so either way, this G2 to -1 is equal to 1. And so now we have groups of 4, and we could then, right, we have this group from column 2, 1, 0 to -1, and now we could group, the next, if we have more bits, 3, 4, 5, and 6 all together, and then group those together to get a group of 8 to figure out the propagate and generate signals. And in that case, this would be the left group, and this would be the right group. To get the generate signal, we want to know, well, is it generated in the left or generated in the right, and then propagated through the left. Propagated through that left. And for the propagate signal, we want to know, well, will both sides, the left and right, propagate it? Okay, so now we know, in this example here, we know that the prefix G2 to -1 is the same as the carry. So this is C sub 2 is 1. We know that we're going to get a carry out of that column 2 because we went all the way down to -1. So if you remember from our last example, or the previous part of this example, we had G0 to -1. Now we have G2 to -1. What happened to G1 to -1? We lost the carry out of column 1. Well, so we can actually take subgroups, right? We don't actually always have to take groups of 1, bring them together to get groups of 2, groups of 2, bring them together to get groups of 4, groups of 4 to get groups of 8, 8 get 16. We can actually say, well, you know what? We can just take the column 2 or column 1. So here are column numbers, 1 and column 0 and column -1. We know these values, the generate signals for that, for G0 to -1. And we know that this is just P sub I, right? P sub 1. That's the propagate value for that top signal. And then we also know G sub 1. So now we could write an equation for G1 to -1. Well, it's still going to be that left group generates it, or the right group generates the carry, and it propagates through the left. This is our right group, and this is our left group. And so now we're kind of using a smaller, instead of combining two groups of 2, we're combining a group of 1 with a group of 2 to make this kind of intermediate signal as well. And so in this case we'd get the equation, well, is it generate in the left column, in this case G sub 1, or generate it in the right, G0 to -1, and propagate it through the left, P sub 1. And so then we'd have that prefix as well, G sub 1 to -1, which again we know that's C sub 0, this is C sub 1, this is C sub 2. Our prefixes, when they go all the way down to -1, are equal to our carry out of that column. So C0, C1, C2, and so forth. Okay, so let's look at the circuit for this prefix adder. So here is a schematic of a 16-bit prefix adder. And so we have 3 types of blocks. We have this yellow block at the top, this little black box in the middle, and the blue box on the bottom. So let's look at each of those to start with. The yellow block up here is calculating the column propagates and generates. And we write this as P sub I colon I. So that would mean P sub 0 colon 0. We've just called that P sub 0 before. But because we're now talking about spans of bits, we're going to be consistent and say it's spanning 0 to 0, which means just column 0. G 0 to 0, similar, is just equal to G sub 0, that single column propagate and generate signal. And really in this -1, that's just producing the generate, so -1, which is equal to the carry in of the entire adder circuit. Okay, now after we produce the column propagate and generates, we're going to then, those are single column, now we're going to group them into groups of 2. So we're going to get column 0 to -1, column 2 to 1, column 4 to 3, column 6 to 5, etc. And these are buses, right? So these signals have P2, G2 on them. And this signal has P1, G1. We're going to use those then to calculate the group, or that span, in this case 2 to 1, of the propagate and generate signals. So let's look at this example here. Column 2 to 1 would get P I to K, which in this case is just P sub 2 colon 2, which is P2, and P K minus 1, or 1 to J, where J is 1. So we get P2 and P1, which now we've kind of expanded those names to keep the range consistent. We're consistently using the range for these propagate and generate signals. So now we have our propagate signal for that entire range, P2 to 1, Pi to J. And let's look at the generate. Well, we're going to get a generate out of just that 2 to 1 block, right? We're going to generate a carry independent of anything else if it generates it in the left, I to K. In this case, it's just G2. Which we've called G2 colon 2. In fact, let's erase the P part, the propagate calculation. And now we're going to get, we're going to generate a carry in and of itself, right, in that block, G2 to 2, the left block. We've also called that just G2 in the carry look head adder, for example. So G2 to 2, to column 2 generate a carry, or GK minus 1, which is G1 to J, which is 1. So generate, or did we generate it in the right block and propagate it through the left block, I to K. Then if that happened, right, either of those cases, now we're going to know what G, I to J, in this case, G 2 to 1 is, whether that 2 to 1 block generates a carry in and of itself. So we do that for all of those, and we're going to get P's and G's for 4 to 3, 6 to 5, right, we're going to take this 2-bit span, 8 to 7, 10 to 9, and so forth. And then we're going to take those groups of 2, for example, 6 to 5 and 4 to 3, and put those into a black box, left and right. Right, here's our left, and here's our right. We figure out, well, will that span of bits 6 to 3, right? That's what we're trying to calculate. Will 6 to 3 propagate a carry? Well, if 6 to 5 did, and if 4 to 3 did, yep, then it will. But either way, we calculate that propagate signal for that now 4-bit span P6 to 3, and likewise we calculate the generate signal, those are buses, by saying, well, did it generate in the left part, G6 to 5? Did that block 6 to 5, did that generate a carry? Or did we generate it in the right, G4 to 3, and propagate it through the left, P6 to 5? And now we'll know our generate signal for that entire span, G6 to 3. And we do that for other groups of 4, 10 to 9, groups of 2 gathered together to make a group of 4, 10 to 9, 8 to 7, 14 to 13, 12 to 11, and 2 to 1, 0 to -1. And then we take groups of 4, and 6 to 3 is our left group, 2 to -1 is our right group, 14 to 11, and 10 to 7 is our right group. And so then we take groups of those groups of 4, make groups of 8, and then finally we take the groups of 8, 14 to 7, 6 to -1, and create a group of 16, get all the way up to our group of 16. And then our final block is this blue block, which is our XOR gate. We get G sub I -1 to -1, that's our prefix, or that's also C sub I -1, where those are equal. And we XOR that, that's our carry into column I, and we XOR that with A sub I and B sub I to get our sum for that column. And so that final group here of blue blocks is our sum calculation. And you can see that, you know, for column 0, we can do that immediately. For column 1, we can do that after one stage because we get G sub 0 to -1. And after 1, 2, 3, 4 stages, we actually have all of the remaining prefixes. So we can calculate the sum for all of the columns at that point. And so want to point out here too, so we're looking at groups of 1 here, group propagate and generates for groups of 1, groups of 2, groups of 4, groups of 8, and then finally groups of 16. And so beyond the groups of 2, 4, and 8, we actually have these kind of splinter off things, and we talked about that in the example. We still need this prefix, the ones in between. And so we calculate that by using, not entire groups of, so in this case, not 2 groups of 2, but a group of 1, and then a group of 2, to get, in this case, G sub 1 to -1. And for the other kind of cases as well, we're going to get, for example, G5 to 3 by taking a 1-bit block as our left and a 2-bit block as our right. And then we're going to use that 5 to 3 to calculate 5 to -1. Once we calculate 5 to 3, 2 to -1. Then we get 5 to -1. So we have these intermediate calculations as well, not just 1, 2, 4, and 8-bit blocks, but we also have, right, here's an example, 4 to 3. We take 4 to 3 and 2 to -1 to get 4 to -1. And then another example, 3 to 3, or just 3, and at the left and 2 to -1 is the right to calculate our 3 to -1 prefix. Okay, so that's how it works, and now let's calculate how long it takes to calculate this addition. Well, let's see, we have one adder delay, or one gate delay, one 2-input gate delay, an AND gate or an OR gate to get to this point. So all the signals have gotten to this point. We've got the column propagates and generates. And now each of the stages is going to take, well, what's the longest delay here? It's not one, that's the short path. The long path is 2 gate delays through each of those blocks. So 1 gate, and then each of the stages, log base 2 of n. So we have 1, 2, 3, 4 of these stages that each take 2 gate delays. And then we have one more stage, the sum stage down here, right? This is the critical path. All of these down here are the critical path. And what's that delay? Is that, right? We have this A XOR B coming in, A sub I XOR B sub I coming in, and then we have those XOR'd with the prefix to produce S sub I. This is XOR'd with G sub I -1 to -1. So is that 2 gate delays or 1? Looks like 2 gates, right? We have these 2 gates going through here like that. But actually it's just 1 gate delay for that last, for the blue box. Because these, at time, t equals 0 plus 1 gate, they're here. A XOR B has already been calculated. A sub I XOR B sub I has already been calculated, long time ago by the time all of our prefixes come in. So this last one, right, A XOR B is waiting here at this signal, and so we're just waiting for that last signal to come in through 1 gate delay to produce our sum result, or S sub I. And so we get 1 gate, 2 gates for each of these, 4 stages, log base 2 of n. In this case, n equals the number of bits we're adding together is 16. So 2 gates times 4 times those number of stages plus 1. So let's write that out. We get the prefix adder, or TPA delay, is this delay to calculate the individual or the column propagates and generates, 1 gate delay, log base 2 of n times the prefix delay, that 2-gate delay to calculate the AND OR gate of that generate signal, plus a single XOR delay for the sum to calculate the final sum. So let's compare the adder delays for all these three types of adders, of carry propagate adders, CPAs. So let's suppose we have a 32-bit adder, and our carry look ahead adder is going to have 4-bit blocks. And let's say our 2 input gate delay is 100 picoseconds, and the full adder delay is 300 picoseconds. Well, ripple carry adder, we have 32, right? The number of bits times the full adder delay, because that carry just ripples through each of those adders. So we're going to get 32 times 300 picoseconds, 9.6 nanoseconds. The carry look ahead adder is, well, remember we calculate the column propagates and generates, the 6-gate delays for the PG block, which happens in parallel for all of those blocks. In this case, we have n over k, 32 divided by 4 is 8, minus 1 is 7, times the AND OR delay, plus 4 times that full adder delay as it ripples through that last block, that last 4-bit block. And so for a 32-bit ripple carry adder, this carry look ahead adder is 3.3 nanoseconds. That's about a third of the time that it takes to calculate this 32-bit addition in a ripple carry adder. That's pretty good. It's got 3x speed up there, approximately. And the prefix adder, well, we get TPG to calculate our propagates and generates, that single AND or OR gate, to calculate those column propagates and generates. And then we get our log base 32 of 2, log base 2 of 32, or 5 times, because it's a 32-bit adder now instead of a 16-bit adder, 5 times 200, and then we get our final XOR gate to calculate the sums, and we get a total of 1.2 nanoseconds. Right, we have our 1 nanosecond or 1,000 picoseconds plus 200 or 1.2 nanoseconds. And so we look at this and we say, oh, that prefix adder was, yeah, you know, pretty close to 10x the ripple carry adder, and you know, close to 3x the carry look ahead adder. And so even though it added a lot of hardware, it paid off in this delay of the calculation, right? We really reduced that critical path, particularly of those carries rippling through the addition.